Thank you for joining our fourth webinar in our 5-part Open-NFP Spring webinar series. Today, Nick Vilhoen is going to present Transparent eBPF Offload, Playing Nice with the Linux Kernel. In this webinar, Nick will focus on the basics of getting an XDP environment up and running, a couple of use cases, and a simple demo of Netronome's BPF offload in action. A copy of the presentation, archived replay, as well as any project code will be made available shortly after the webinar. These, as well as our previous webinars, can all be found on the classroom page on the open-nfp.org website. Nick Vilhoen is a software engineer at Netronome currently investigating the use of NPUs in networks analytics. He is working on combining this with OVS Offload on the Agilio platform, as well as developing machine learning-based approaches for handling predictive network control at high data rates. Let me describe Open-NFP before I turn it over to Nick. Open-NFP's objective is to support and grow reusable applied research and technology development in data plane network functions processing. We do this by focusing on reducing the barriers to performing research in this space to researchers and developers, creating, implementing, and verifying their ideas on production networking hardware. Open-NFP supports research in a wide range of technologies, including software-defined networking, OpenFlow, Open vSwitch, and P4. We support researchers with a variety of tools, including deeply discounted hardware, IDE software, and cloud access to development systems and direct support from our engineers and our research community. We also provide support to learning advanced networking concepts on our hardware through tutorials and seminars, such as the one we are performing today. We encourage proposals to research funding agencies. We invite you to join the 40+ universities and companies working directly with Open-NFP through projects. Over to you, Nick.
I'm having slight connection trouble in the office, so I do apologize if at any point I become unclear. So I will start off, and if there's any issues, please somebody let me know. So today I'm going to be talking about BPF and XDP, and I will just this is going to be a very basic talk. We're going to be going across the sort of the simple issues, and really the aim is going to be to help you guys have some comfort level and some basic understanding of how everything fits together, and also be able to do some simple work, and maybe be able to get some simple programs running, and also understand how to get the performance which people promise you with BPF and XDP combined. So those are really the objectives of this webinar. So first, we're going to be going across the basic architecture of eBPF, what it is, the programming model, and how it hooks into the kernel. Then after this, we're going to be going and trying to give the user a basic understanding of XDP, what it is, where it sits, how to use it, how to get the sort of performance out of it, as I said, and finally how to offload it. So what actually is eBPF? eBPF is a simple way to extend the functionality of the kernel. It allows you a lot of flexibility and a lot of dynamic, it allows you to use the kernel in a very dynamic way while still having the safety of the verifiers. The BPF verifier is a key piece of this whole puzzle. And what it gives you, it effectively gives you a small virtual machine in the kernel, or a machine in the kernel. You have 10 64-bit registers, you have a 512-byte stack, and you have these data structures which are known as maps. Now, in theory, these are of unlimited size. However, obviously, that is limited by the size and performance of your computer and what you have sitting behind it. And to be clear, this is something which, what I haven't mentioned here actually is that this is part of the Linux kernel. So the full BPF system with the hooks in the XDP and also a lot of the other stuff, really this is still something which is developing in the kernel. So we're still talking about new XDP actions. We're still talking about new helper functions. We're still talking about a lot of new things to do with BPF in the kernel. So this is something which is developing in front of our eyes today. And the final part of this little puzzle is that the size of the program is limited. So you can only have 4,000 BPF instructions, BPF bytecode instructions per program. You can also have tail calls, so you can link up a bunch of programs. I think you can link up to 32 programs from memory right now. You are also limited in the amount of maps you can have. Now, all of this will probably not mean a lot to you right now if you don't know much about BPF. The other final point to note is that it can be jittered to maximize performance in the kernel. So what we're going to do over the next probably 30 or 40 minutes is just deconstruct all these statements. What are these things? How does this fit together? And how do you, as a software engineer, how can you actually use this? So to be clear, this is something which is used today, and this is used within hyperscale. So these are the people who have publicly spoken about using BPF. So Facebook have spoken about using it for load balancing and security, and have said they are actively using it. Netflix use it for network monitoring. The Celium project is part of Cisco as an orchestration platform for containers. It's actually won a big prize from Google this year. So Daniel Borkman, who's one of the guys who built up that system, has got a lot of acclaim for it, and he's doing a lot of work in BPF right now. Cloudflare have spoken about using it for security as well, and finally OVS have said they're exploring it for virtual switching. Because of the fact that this is upstream, and you have that knowledge that you have the kernel supporting this, it does provide a safe, flexible, and scalable networking tool which you can use. Next up, the programming model. So this is just to give you an idea of how, okay, great, we have this thing called BPF, we have this machine, we have this sitting in the kernel. How do we actually use it? How does it help me? So what you have is LLVM is able to, I don't know why there's a space in the middle of LLVM there, my apologies, is used to compile from supported languages. So there are some simple support for Go and P4. So VMware have actually said that when they're building the OVS offloads and when they're working with OVS and experimenting, they're actually experimenting in P4. So this gives you a great sort of linkage between P4 and BPF. So you're able to write in P4. You're able to write, some guys have actually started working on a Go compiler in Europe, and this seems to be taking off as well. And finally, you can write in C, which is sort of the standard, the de rigueur way of doing it. And these will get compiled by LLVM into an L file. And then when you load the BPF program, which is something we will look at later, you have the program go through the verifier, which ensures the safety of the program, and then you either have it jittered and it sits within the host CPU, in which case you get very good performance, or actually what we've upstreamed at Netronome, here at Netronome, is we've actually upstreamed the NFP BPF JIT now. So you can actually offload your BPF programs to the NFP hardware. And we reuse a lot of the infrastructure within the verifier to be able to do this. So this gives you a way of doing this even when the performance, you are struggling with performance in the kernel. You can actually offload certain BPF programs to the NFP. Now, to be clear, today I'm not going to be speaking a lot about the offload. I'll quickly mention it at the end. I have a little slide which I can show people and can give you guys sort of a taster. But really today is just going to be focused upon the basics of BPF and to get you up and running and playing with something in the kernel. So the next question is, so now we understand that we write a C program, we push it through LLVM, and this gives us some bytecode, and that bytecode runs in the kernel. Now the next thing is, how do we get this to do something useful? To do something useful, we need to be able to talk to it, to read it from user space. We need to be able to control it from user space. And we also need it to be able to actually provide information. So for this, we use the maps. Now, what are maps? They're key value stores, which can be accessed from both kernel or user space. And they are, as I say here, used for interactions between the kernel and user space programs. Now, there's a number of different types of maps which are used in different situations. So you have very simple array maps. You can even have program array maps, which have an array of different set of programs which are running. Then you can also have actually per CPU maps. So these are used for efficiency in certain types of DDoS filtering programs or load balancer programs, other programs that need high levels of efficiency low down in the kernel. And we also have had a recent addition which Martin Lau from Facebook did, which was actually the LRU maps. So this is a mechanism whereby the least recently used entry within the map will be deleted. This ensures that your maps don't explode in size. You have a limited size map, but you also get the most efficient usage out of it. So okay, great. So I have my program. I know I write a bit of C code. I then compile it to LLVM. I know that I use these abstract concepts called maps to interact with it. So how do I do that? How do I create these maps? How do I use them? So I'll run through a more full program example later on. But just to show you quickly how you can create maps and use them. Now, this is a big oversimplification. There's a lot of other things you can do, but I just wanted to give you guys two little options and two examples just to get you kicked off. So what we have here is we have an option on the left, which is you can just use the you can use a syscall to create a map. So this is something which you can do. So you can see on the left-hand side here, we create a union BPF map attribute, and which decides the map type. So we'd put in values here, like the map type, the key size, the value size, and the maximum amount of entries. And then we decide to create a map, and we use the file descriptor, which is this attribute here. And we define the map, and we define a map which is the size of which is required for that set of BPF attributes. So that will help us, and that will actually allow us to create that map. Now the second option is the one here on the left, which is something actually using some sort of special things within the compiler. But if we use the elf attribute SEC here, so we define a structure called BPF map def, and then we call it with sec maps, which is used by elf, and then within here we define our map. So the example here we have BPF. We define the BPF map type. We define the size of the key, define the size of the value, maximum entries, and any flags associated. So this is just giving you a simple example. Now this is not yet enough, but this gives you a simple overview of how you can start building a map. So just before I get on to the next things, I just quickly want to do a quick detour. This is a quick dive into the weeds. I won't go any deeper than this right now. What we have is we have the bytecode. So just to give you a few quick examples of how the eBPF bytecode fits together. So some of you might remember the original BPFs we had, what's now called classic BPF or CBPF, from the early 90s. Was a very simple machine with two registers. Now, as I've described, eBPF is significantly larger, and the bytecode is also a bit more significant. So a bytecode instruction is a 64-bit instruction, which divides up into an operation code, which is 8 bits, a destination register of 4 bits, a source register of 4 bits, offset of 16 bits, and an immediate of 32. So the operation code divides up. So that divides up into the, sorry, what I've called here the operation code. Well, there's a slight oversimplification here. The opcode, which is 4 bits, which involves the, either it's something like a BPF move instruction, BPF jump not equals. There's many other different instructions as well which go within those 4 bits. So these are the first 4 bits of the bytecode instruction. We then have a 1 bit which tells you which source it is. So it's either using the source reg and dest reg if it's BPFX, or if it's BPFK, it's using the destination register and a 32-bit immediate. So finally, we have the instruction bit, which is instruction class, which is 3 bits. Now, these issues may seem as arcane, but over time, as you guys build up programs, you guys may realize there are issues in the verifier, there are reasons you can't get your program through, and then it becomes very important to understand what the verifier does. And these are attributes, these are parts of your code which the verifier uses significantly. So being able to just quickly understand this stuff is very useful. Now I've got some references at the end which will help you if you want to dive deeper into anything such as the bytecode, such as the maps, or any other aspect of the system. That will allow you to do that. And here are just a couple of examples of bytecode instructions. So in the first one, moving the contents of register 1, which is a source register, to register 6, which is the destination register. And also notice that we have a 2-operand system rather than a 3-operand system, so that we have only a source and a destination register. We don't have 2 registers which get acted upon and get stored in a 3rd register. So when you use an immediate, use the immediate as well as the destination register. So in the second example, we're actually jumping 11 instructions forward if the contents of register 1 is not equal to the hex value used. So there are many places in the kernel whereby we can hook in. So what we've done now so far is we have a very quick understanding of how the maps work. We have a very brief understanding of how you would program a C program and create bytecode, and we have a small amount of understanding of what the bytecode looks like. Now the next question is, we have this entity which is the BPF program. Where does it go? What does it do? We've created this thing and it's kind of this blob, but we need to hook this blob in somewhere, otherwise it's useless. So one of the key things about BPF, and I'll show this when I show you guys a little example program a little bit later, is that we have different parts of infrastructure inside the kernel which we can use with our BPF programs. So if you are, for example, if you're in the socket filter world, or you're in NetFilter, or you're in TC, you have some infrastructure. So in TC, you have the SKB, well, you have the SKB all the way up the stack, except for XDP, which you can use. And then you also have XDP at the bottom of the kernel, which is designed as a super fast place to be able to run small, flexible BPF programs. So it gives you a bunch of places you can hook in these programs with different infrastructure involved. And this will allow you a lot of power when you're using these programs. So next up, now what I want to focus on. So we have a very brief overview of the blob, as I call it, the BPF program. Now we need to understand the infrastructure which goes around. Now I'm going to focus in this talk on XDP because XDP is something which is very interesting in terms of the power it gives you to do DDoS filtering, load balancing, and potentially very, very interesting other applications in the future. As XDP redirect becomes more powerful, it may be able to work as a tool to effectively have very low latency page flipping of packets into user space, which will allow you to, while still being kernel safe and upstream, get packets to user space very, very quickly. But that's something for the future. Today, the main use cases involve DDoS protection and load balancing. So XDP programs have none of the XKB infrastructure there before SKBs are added to the packet, which is what makes it so powerful for DDoS, because you're able to drop packets as soon as they enter the driver. And also for load balancing, because a lot of time you want the packets which are being load balanced to head straight back out the system. It's inefficient if you actually end up pushing them up the stack, spending a bunch of compute cycles adding the SKB, spend a bunch of memory storing those SKBs, and then just push the packets back out and detach them. So what we're doing is we're saving a significant amount of CPU cycles by using the system. Now, also the other thing is the XDP metadata is extremely simple. Just start of packet, end of packet. That's all we have. And we are allowed to add a maximum of 256 bytes of prepend to the packet. So if you need to send information up the stack, that's what you can use. If you need to send information back out, so let's say you have a packet which is just coming in and being TX'd out the same port, which is what XDP TX does, you can actually add information to the front of that packet if you want to be then passed by, let's say, an XDP program somewhere else, as long as it's directly linked, and as long as it's safe to run through the network. It gives you a lot of power which you would not have had before while still running in the kernel. So this gives you a production-ready system to utilize a huge amount of flexibility within your network. And being able to do that gives you a lot of power. So what I'm going to do now is I'm going to go through a very simple example, which is one of the kernel sample programs. So this can be found in recent kernels, 4.8 plus, in Linux samples BPF. I'm actually going to show you it on GitHub, just to show anybody who doesn't want to go hacking around in their kernels or finding a kernel which is 4.8 plus, that actually getting this information doesn't mean that you need to be on the latest and greatest kernel. You can, as an interested party, go and research this stuff before you take the plunge and upgrade to 4.11 or 4.11 RC8, I think we're on now. So I'm not going to go through this line by line. If you want more details of this stuff and actually get into the real guts and want something a little bit more advanced, Andy and Jesper had an awesome tutorial at NetDev. Now, I've just realized I've actually forgotten to put this directly into the links, but I will make sure it's added before these slides go on to the Open-NFP website. And then you guys can click on it there and check it out. So this was the recent NetDev conference, which I'd highly recommend to anybody who's interested in this stuff. It's a fantastic conference, and it's highly academic, and there's a lot of great talks, and people are very accessible. So I will send it. I'll make sure there's a link to their tutorial added into the links. So at this stage, without further ado, let me just quickly try and context switch here. So, no, I don't want to leave the webinar. What I want to do is I want to move to Safari. So can you guys, I just want to make sure that hopefully everybody can still see my screen. So I'm just going to run through very, very high level quickly through this example, which is the, it's called xdp1_kern.c. in the samples BPF repo. Now, the first thing I want to just point out is that, as you can see here, we're using a lot of standard kernel infrastructure. We're using header files from other places. So you're not isolated, and you don't have to build all your own infrastructure. You can use, if you're in the, if you're higher up the stack, you can use more of the infrastructure. But the standard C infrastructure you can use. So in this example, it's actually being used, as you can see here, to pass IPv6 packets and IPv4 packets. And we're also doing, as described earlier, we're actually defining a map here. So as you can see, we're actually defining a per CPU array map, which is a small size, but it gives you an idea of how to do this. And notice we've given it a file descriptor here. So the other thing to note is that in BPF, you are not allowed loops which could potentially be infinite. So everything needs to be unwrappable. Unless it's unwrappable, the verifier will not allow it. So this is something which I think a lot of people, when they start using this, run into. And they don't understand why their BPF program why the verifier won't let the BPF program through. If you have back edges in your program, in compiler terms, effectively full loops, then your program will be unsafe, because it is possible for you to create something which could hit an infinite loop and cause a lot of damage to your machine. Now, to be clear, there are still definitely things allowed in BPF which would cause some damage to your machine. But the verifier ensures that you need to be fairly good at breaking things to be able to do that. The verifier gives you a lot of safety. So as you can see here in our main program, we have, first thing to notice is it's no loops, simple, very short program. If-else statements ensure that we just keep falling through. You'll notice here that we define XDP drop here fairly early on. And then as we go through, we will check for different types of packets. So we're looking here with VLANs. So we're seeing if the packet is not safe, we will drop it. And again here. And then we pass through the packet. And in this example, we end up doing a lookup. And then we return the value, which comes from the lookup in the map. And then eventually we drop the packet as well. But in that, we are actually incrementing, I believe, somewhere the a counter. And then we also have a user space program which goes with it, which interacts with the map from the other side and actually builds up a per protocol drop counter in user space. Now, as I said, I'm not going to go through this in detail right now, but this gives you a good idea of what a BPF program will look like and what it will do. So you can see here in the user space program, we're allowed loops. We're allowed to do all this type of stuff. We're allowed to access the maps in that way. So the kernel program has to be extremely safe, no loops, but in user space, we're allowed a lot more flexibility. So you can actually build your app up in user space, which is simply using this kernel infrastructure to gain information or to add security or to add some simple features. So you can run your orchestration, you can run all your high-level logic in user space, which is more complicated, which requires more complex loops and other types of programming structures. But you can actually run your simple program inside the kernel. So let me now return. So the next thing to do is to understand slightly how to optimize XDP. So this is something which could happen very easily to people. They start using XDP. Let's say you had let's say you're not offloading XDP. We're not talking about offload at this stage. Let's say you're running with a Netronome NFP, and you plug in your NFP. You run basic NIC or core NIC firmware, so the packets are just passing through the NIC, and then they reach the driver, and you're doing it, let's say, just XDP drop or XDP TX, simple tests, and for some reason you aren't seeing the performance that people claim. Now, why could that be? There's a bunch of different reasons for that. This list is not comprehensive, but when you get to these types, when you get to this level of optimization, you need to be very careful. So if you do the steps above, this will probably give you some level of assurance and some level of performance in terms of what you're doing. It may not give you the optimal performance yet. You might need to do a little bit more tweaking on your local system, but this will give you a lot of advantages. So the first thing to do is to ensure your BPF jitter is actually enabled in your kernel. Now, this is the first thing people run into. If you're running the late enough version of kernel, you're running a recent kernel, everything else seems right. You are pinning your interfaces, your ring sizes are optimal, yet your performance is, let's say, 8 million packets per second for drop. What's going on? What are you doing wrong? You have to ensure your BPF jitter is enabled. Otherwise, you will not compile down all the BPF bytecode into x86 assembler instructions. So the next thing to do is also ensure that the queues that are connected to the interfaces on the NIC you're using, whether that be a Netronome NIC, whether that be a Mellanox NIC, whether that be, I'm trying to think who else has XDP support at the moment. I think QLogic, Broadcom, whoever that is, Intel will soon. You can use any of those NICs, but you have to make sure that you pin the queues to the interfaces, and that's going to be fairly significant in terms of performance. Also, make sure your ring size is at an optimal level for your NIC and your application. So if you're running a bunch of jumbo packets, your ring sizes and so on are going to be very different to if you're looking at 78 byte or even MTU size packets. And yes, to gain some level of your performance, what I've alluded to, you need to ensure that you have just simple XTP drop and XTP retransmit programs. Many people use single core performance as a fairly reasonable benchmark of how well optimized the driver program is they're using. To do this, you need to use the eth2x command, which will ensure that only certain queues are actually taking packets. Now, I will show an example of this now, straight after we finish this slide. And the final thing, just a big duh, is that you will not get the simple program performance if you build something complex. So if you see drop of 30 million packets per second, if you build a hugely complex DDoS filter, surprise, surprise, you're not going to get a drop rate of 30 million packets per second because of the fact that a huge amount of processing is being done to actually run through your filtering system. This is something which needs to be understood, and this is something which people need to appreciate, not only with XTP, but also if you're using DPK, if you're using BPP, if you're using any other system. Simple performance benchmarks are not enough. You need to actually understand what's going to happen when you build a more complex program. So that's something we need to understand when we use this type of infrastructure. Okay, so what I'm going to do now before we get to offload is I am going to exit full screen, and then I'm going to go to my terminal window. So I actually currently have a system running. So what we have running here right now is XTP drop across a multi-core system. So just to run through some of the things you'll see in my little, in the little app we have here to do the watching. So these are various counters within the system. So you can see here, our packets are fairly well spread across 8 different queues here. So these are the RX packets all coming in, and they're all being dropped at the moment because we're running a drop program. So as you can see, all these programs, all these counters are fairly solid. Now the question people might have is, oh look, why is my RX drop counter 0? This is unsafe drops. So if they're being dropped by XTP and they're being dropped in a safe manner, they won't show in these counters. So what I've got here is I've got the device under test connected up to an Ixia, which is a very, very useful tool, and I would recommend anybody who wants to do this type of testing seriously, this is a great tool to use. Highly recommend it. And so what I'm going to show you is I'm going to show you the drop performance here. I'm going to show you some of the commands we used to check the queues, check the queue sizes, make sure everything is safe, check the ring sizes, and then also how to load up XTP programs and how to look at the performance numbers. Let me exit this. So what we have is we have some simple programs we have already built, and we're going to load them. So at the moment, we have drop.ro running. So this is the command. So another key thing to note, and something I forgot to put down on that slide, is that you need to ensure you're on the right NUMA node as well. So if you have a system with separate NUMA nodes, you need to use NUMA Kernel to ensure that everything you're running is on the correct NUMA node. So remember that very, very, very loud and clear. NUMA Kernel is utterly essential for this type of work. So what I'm also going to show you is just quickly how to, so this is how we do the weightings for the different queues here. So as you can see at the moment, I have 8 queues, and my weight is spread evenly across all of them. And I have different cores pinned to different queues. So let's quickly have a look at that. So let's look at that first, actually. That's probably the best thing to start with. So the first question is, how do I know which queues in my system? So you're going to have more queues, and you're actually going to have queues linked to your NIC. How do I know which queues are linked to my NIC? So I know which queues to pin. So you use this command, So grep across eth4, so eth4 is where my NIC is right now, so we see that with ifconfig, and we grep for rxtx like this. And this is a very messy output, but it does show you what you need to know, which is that, and bear in mind this is a multi-thread system. So thread 0 is attached to this core here. So we have IRQ soft queue 51 here. We have 52, 53, all the way up to 70. These are the ones being used, and as you can see, the counts go across the page here. That's due to it being the different cores which are attached to the different interfaces on eth4. So we can see eth4 is attached to each of these. So this is what we're actually grepping for here. We're looking for eth4 and we're looking for rxtx. So this gives us the information to then go to, I'm just going to cd8/proc/irq, and in here we will see a list of the different IRQs we have. So this is what we mean by pinning the cores. So we would see we have 51. So let's go to 51. And then we look for SMP affinity list. And as you can see, we have 0 there. So this is attached to the first core. And then let's look at Now remember, we have hyperthreading here, so we have 2 threads per core. So that's something important to remember. So then when we go into 52, which is the next queue, we should see this attached to, I think, 2 because of the fact that, yes, so 2 because of the hyperthreading. So 0 and 1, 2 and 3, 4 and 5 will be attached across the various cores. So that's what you need to do. So you might go into your system and see something. Let's see, I haven't tested this, so if this goes wrong, I apologize. But let's see if we look at IRQ0. Let's go first. Let's see if we look at IRQ0. We can see in here, hopefully, that this one is attached across the different cores. Yep. So this is attached from 0 to 19. So this is across both NUMA nodes. So CPU core 0, CPU 1, CPU 2, CPU 3, CPU 4, all the way across the second NUMA node, which goes up to 19. This soft queue can send packets to all of those. So this is not pinned to any specific CPU core. So this is probably what your system is going to look like when you start. And then you need to say, okay, this queue is attached to core 0, this queue is attached to core 1, etc., etc., etc. And that is what you need to do to be able to get this up and running. So I'm going to exit this. So we now know how to pin our cores. So we've pinned our cores. We then also need to, before we do anything else, we need to make sure our ring size is appropriate. Now, apologies, for some reason my history is gone. Oh no, there we go, we're back, I think. So we're having, okay. So luckily I did something just in case this happened. So I did save a bunch of the commands we need over here. So I will see what goes on there. So what we need to do next is we need to set our ring size. So here I've just got an example of a ring size command whereby Rx is being set as is, and then we're setting our TX ring size to 2,400, well, basically 2 KB. So that gives us the ability to dynamically configure this. So we want our NUMA kettle is important, and then it's eth2-g, and we can use, and then we set the interface, and we set the numbers for Rx and TX. We could also just easily set TX to 2048 as well. So that now we've set our ring sizes, we've found the queues, we've set the queues, we've pinned the queues, sorry, we've pinned the cores to the queues, and now we have our BPF program running, and apologies, I don't know what's happened here. I think I may have lost network connectivity. Well, no, I haven't lost network connectivity as long as you're all there, which it seems. So I'm going to set up a new tab. I think my machine may have just died briefly for a second there. So let's see if I can get back to it. Now I've got to remember what its address is. So this is from memory, so I apologize if this goes wrong. Bear with me for 1 second, please. Sorry, guys. Okay, everyone. I'm very sorry. I'm afraid I'm not going to be able to show you anymore. So I've just heard that our connection to our office in Pennsylvania has gone down, and unfortunately, that is where the servers are. So I'm afraid I'm not going to be able to show you anymore. I will try at a later date to quickly show you, so you can demonstrate, so I can demonstrate some numbers to you guys. Yeah, I'm afraid there's nothing I can do about that. So I apologize for technology defeating us there. So let's go back to the slides. So my apologies. So what I can show you is just as I've shown you guys here. This is the other very important command to bear in mind, which is -eTool-x. So this allows you to look at what to do with so to do single core optimization. So if you want to look at single core performance, you can look at this. So I've just had a thumbs up, so maybe PA is back. Let's see. Let's see. Let's see if PA is back. That shell doesn't. Let me just quickly, excuse me for 1 second. I will make sure the PA is back, and then we will see if we can get this up and running again. So I do apologize about the brief delay. We are back on the road. Okay, this looks good. Yep. So we are back on the road. So let's go full screen again here. So where are we now? So where were we? So let's quickly set up. So we are doing some single core tests. So what I need to do is let's just type it in manually. I'm just going to freestyle this instead of going back in commands for speed. So let's just do this. Actually, I need to, let's just make sure. I'm just worried that I get something wrong and then everything goes wrong, and I don't want that to happen. There we go. Yep. Okay. Yes. So I would have messed it up because I forgot to put in the interface. So now we've set it so that we're only using a single core, and this will give us some information in terms of how optimized our performance is, because when you run across many cores, as you saw, we actually run into other bottlenecks within the system. So we're not able to accurately assess the performance of XTP within our driver. And now, in my apologies, I seem to have the go to webinar across the phone. There we go. So what you guys can see now is this is the amount we're able to actually drop with a single core. So as you can see, all the packets are going to one single core at the front of the system. And this gives us some very nice performance numbers. So as you can see here, with a single core in the kernel, we're able to drop 25.8 million packets per second. That's with a single core. And we can quickly, if we have time, we can quickly I will very, very, very briefly do a quick TX test as well, just to show you guys. So we're going to set our system back to, actually first we'll do a TX with a single queue. So what we'll do is we will go up to, so I'm going to do this. I'm going to draw our XDP, and then I'm going to switch drop.o to tx.o. And so this is the command to actually set the XDP program. And now we should be doing tx on a single queue. So now let's check out what it looks like. And yep, it worked. And as you guys can see, it's we're actually txing and so we're receiving and transmitting 20 million packets per second bidirectionally here with a single core. And this is really impressive to be able to do this within the kernel. So this is showing that XDP gives us a great way to actually do very high performance packet processing while still being upstream safe, while still being kernel compliant, and this gives us huge benefits in terms of maintainability, in terms of actually using this in the future, and not being stuck. So the problem is, as soon as you go outside of the kernel, you can end up in a position whereby technology you have is not maintained, systems aren't kept up. Red Hat has, as you know, their guarantee for their kernel systems for 13 years. 13 years of support. They provide this because they're confident the upstream community will keep supporting features. That's why they're able to do this without too much risk themselves. And this is the advantage we get with XDP. We get the best of both worlds. We get the performance and we get the reliability and support. Now, what if this isn't fast enough for you? What if you end up building a very lovely program and it's a little bit too complex for the kernel to be able to run at those kinds of speeds? So this is why we've offloaded XDP. We've upstreamed our initial version of this, which is the NFP BPF JIT. You can check it out online. It's in the kernel. You can check it out on the mailing list. I'd credit Jakub for that, who's sitting next door. He's the main inventor behind that, and he's done a great job. He's also the guy who's optimized a lot of our XDP in the kernel, which is why we're getting fantastic numbers, which I'm very proud of. Finally, just quickly running through the offload architecture. So the yellow bits are the bits we've modified. So we created the JIT. So effectively what happens is that you push your XDP program into the driver, and it gets offloaded down into the hardware by the JIT. We've made some changes to the verifier so we can re-verify programs. And once that is done, we push everything down, and it's been re-verified. So sorry, the reason the re-verification is important is because there might be certain types of programs accessing certain types of maps which we do not want to offload. There might be many reasons for this. For example, if you, in the future, if XDP redirect becomes a viable way to push packets up into user space, that wouldn't be very useful to offload if you didn't want to push packets directly from your NIC to user space in the first place. So that plus different types of maps, there might be types of maps which we don't want to offload. Kernel tracing isn't something we're looking to offload too soon. So there's going to be lots of different types of programs which aren't offloadable. And we need to be able to check that when we're running through the verifier, when we're running through things in XDP or TC. So here are just some references, some interesting documents. I'll add the other links to this as well before I push it online. Quentin actually has got a very useful reading list here, which is very good to use. Jesper Danhard Brewer has written some great documents which are very useful as an intro. I actually find the kernel docs are great as well if you want to actually understand how the structure fits together. And also the other link I've put here is the initial XDP presentation from Alexei and Tom Herbert, which is also very useful to understand, to explain where this has come from in the first place. And then you can also always type in BPF on Google and things turn up. So that's pretty much it from me. If any of you guys have Any questions? Please, now is the time to fire away.
I don't think anyone has any questions. If you do, feel free to reach out to either myself or Nick. Thank you, Nick. And again, this webinar, as well as all of our previous webinars, will be available on the classroom page of the OpenNFP.org website. Thank you all for attending.